Sometimes we want to approximate a solution to a problem numerically. This is especially true when the equation is too complex or even unknown. Euler has a method for initial value problems. Suppose you have a differential equation y prime equals f of x y with the initial condition of y of x naught equals y naught. We increment x slowly using the index n, where n is an integer, to count the number of steps taken. This gives us the equation x sub n equals x sub naught plus n times h, where h is the step size. Y is incremented as a series of linear approximations. To increment y, we use the equation y sub n equals y sub n minus 1 plus h times f of x sub n minus 1 y sub n minus 1. Consider the equation y prime equals 2x plus 3y plus 1 with initial conditions y of 2 equals 0. Use Euler's method with a step size of 0.1 to generate an Euler table. Go from x equals 2 to x equals 3. Our initial conditions are n equals 0, x sub n equals 2, and y sub n equals 0. We start by calculating for n equals 1. So, x sub n equals 2.1. Then we'll find y sub 1, which will be y naught, 0, plus h, 0.1, times f of x naught, y naught. This evaluates to y sub 1 equals 0 plus 0.1 times the quantity 2 times 2 plus 3 times 0 plus 1. Altogether, y sub 1 equals 0.5. We can calculate the rest of the table up to n equals 10. At n equals 10, we have x equals 3 and y equals 23.5. On the right is a graph of the original function f of x solved from the differential equation. It is graphed from x equals 2 to 3. F of x is graphed in blue, and the Euler approximation is graphed in orange. The Euler approximation has the same shape, but since this function grows so quickly, its approximation power is growing worse. We can see that when n equals 10, we have y equals 23.5 on the graph of the Euler approximation, but the actual function value when n equals 10 is about 35. We can see from looking at this that it would probably be best to use a smaller step size if more accuracy is needed.